Maybe more something.
First, I'll begin with some comments on quiz 1.
Quiz 1?
I'll give you
Quiz 4.
I'll give you.
Quiz 4.
Quiz 4. Quiz 4. Okay, so the first comment is read instructions carefully. It's one of the reasons why people lost a lot of points in the first test. So, for example, here, that's for the equation in Green's theorem. Something that you write down must be an equation. So it's not good enough to write down one side of Green's theorem. You have to write down the whole equation.
That's why
Right, so, yeah. Reading instructions carefully is something that's obvious why that's important, right? I mean, in school it might not look like a big deal, but in the real world, when you have a problem that needs to be solved and you need to really pay attention to what's going on, you need to really listen to what whoever's employing you wants, right? If you don't get it done, you get fired, right? So read instructions carefully. It's one of the reasons why I'm so anal about how you hand in your homework. If I say I want the topic number and the section number, I want the topic number and the section number. If you don't give me both of those, I'm going to take off points, because following instructions is important. Okay. Another comment is from problem 4.
Which test?
Same quiz 4.
No, but it was A and B, so I can switch around.
It's both sort of the same thing, right? Problems with the C. Okay, so I can do it because I don't remember which one it was from which. But there was one where I asked about the second quadrant. Right? And there was a quarter circle in the second quadrant of radius 2, right? And I said C, so it's a disk, so you know stuff is filled in. You could have shaded this in.
Okay.
And I said C is the boundary of the region, oriented clockwise. Now what is the boundary of this region?
The x and y axis and the line.
The x-axis, the y-axis, and the circle. If you only put an arrow here, I'm going to assume that this is your C. It's not your C. It's a part of your C. That is the correct answer. Your C is all curves surrounding the region.
So be careful.
Be careful. And I even had some people, they bolded this part, right? To say, oh, that's the C. No, it wasn't the C. That's only part of the C. And this is the sort of mistake that in test 1, a lot of you are forgetting curves because you don't even know how to draw the picture. Right? C was the boundary of the region. Do not forget curves. Read very carefully to realize what the C is. Right? So a lot of people, so if, for example, if I had asked this in an exam, in a bigger exam, and I asked you to like compute line integrals,
that'd be wrong.
Most people would have done only this curve and just moved on because they would not have realized that you had to consider these two. So if I asked you to do a line integral on this guy and equate it to Green's theorem, you had to do these 3 curves, right? Putting an arrow on one curve shows me that you're only considering one curve. It's not one. It's the boundary of the region, the total surrounding. So yeah, a mistake like that would cause the mistakes that you did on the first quiz. So don't be like, you took out a point just because I didn't leave out the arrows. It's a big deal, right? It cost you guys a lot of points in the first test because you forgot those arrows. Okay, let's see. Okay, some people, I don't know what this was, but some people, they drew a circle and a line, and they shaded something like here or one of the, I don't really know what happened there. I can't really comment. But
What is that?
yeah, that, no. It should look like this, only a quarter of the circle. I don't know, I didn't know what that line was about. Let's see. And of course, pre-calc mistakes, so just so you guys cannot say that Jhevon never told you, let me explain once and for all. you have an angle that subtends an arc length that is equal to the radius, this measure of the angle is called a radian. Okay. There are 2 pi such radians in a full circle. Right? So, right? Just a pre-calc lesson. Okay. It means that if you have a quarter circle, there is a quarter of 2 pi radians in that circle.
Okay.
Okay. So. So here's my circle in R2. This is the angle where the angle is 0. When I open to here, what's going to be the angle? Pi over 2. That's correct. See, you guys are so smart. Okay. So if theta is the angle of here, what is the range for theta that defines the first quadrant?
0 to pi over 2.
0 to pi over 2. That is correct. Okay. What about over here?
0 to
Pi
pi.
over 2.
Pi over 2 to pi. That is correct. What about over here?
Pi to pi over
Pi to 3 pi over 2. Okay. What about over here?
pi over
3 pi over 2, 2 pi.
You guys are so smart and so smart. Look at that.
Do we get points
Okay.
back?
No.
Come on, help me out,
Okay.
you guys.
Now, quadrants are numbered according to the following convention.
Okay.
The first quadrant is the top right corner. This is quadrant 1. Quadrants are successively numbered going in the counterclockwise fashion. So this would be quadrant 2, this would be quadrant 3, this would be quadrant 4. Is everyone with me so far?
Interesting enough, navigation goes the other way around.
Yeah, interesting. Does everyone understand? Does everyone really understand?
Yes.
If you have questions, let me know. What's your question?
For number 4 in the setup, can you just run through it real quick because there's like negatives going on there.
Oh, well,
so it
okay,
gets
I'll
confusing.
talk about that a little bit more. But
Okay.
I want everyone to understand this.
How come for navigation goes the other way around?
Huh?
How come when you go
All this is a
compass-
convention. It's a convention.
Yeah, true. But
People just decide we want it to go this way, and then they base all their calculations on it.
Yeah, but
It's
why did
convention.
they have 2 different chooses? Like, if you have a
Just
compass-
because they want to be difficult, I guess.
Okay.
I mean, if you go to like physics or engineering classes, then in spherical coordinates, your theta is the phi and the phi is the theta. Why they decide to switch the 2 things, I don't know. It's just convention. Right? Anyway, here, these are the quadrants. Does everyone understand?
Sure.
Because from your quizzes and your tests, it's clear that everyone does not understand. Right? If I mention the second quadrant, where am I talking about?
0.
Over here. If I say the third quadrant, where am I talking about? Over here. Does everyone understand? Okay. Any of you make a mistake with something like this ever again, so help you God. I will take off more points than the question is worth. You will not be making mistakes with these pre-calc questions. This is not something difficult. This is something you should know. This is something you should know 2 years ago. Okay. People still don't know all the quadrants and what angles are in between the quadrants. So I'm seeing integrals being set up 0 to 2 pi, 0 to 3 pi over 4, all sorts of weird angles when
Okay, well, you're going to divide by the number of that.
that's that. Someone asked about the fourth problem, so let me just run through that quickly. Let me do from quiz 4A. The other one is very similar, right? In part A asks for the second quadrant, in version B asks for the third quadrant, and the functions are a little bit different, but yeah, so I said the quarter disk x² plus y². So that's defining a region because I have an inequality. And I want the second quadrant. And C is the boundary. So we have a circle, and some people actually draw a full circle and put arrows all over the thing, which was wrong. All right, so you have a full circle, but I only care about the part in the second quadrant, so there's only this part. All right. C is the boundary of this, meaning the surrounding area, and it's oriented clockwise. This, this, this is 2, this is 2. And then you can shade the area. Okay. So that was part 2. If you shaded the right area, which not everyone did, but forgot the arrows, I only gave you 1 out of the 2 points. If you did the arrows and didn't do the shading, I gave you 1 out of 2 points. You had to do both the shading and all the arrows to get it correct. There were about 2 people in the entire class who got that correct. Out of 35 engineers, only 2 of them knew to shade the correct thing for the second quadrant. How many engineers did it take to screw in a light bulb? Okay, let's see. So in problem 2, I actually derived down the equation for Green's theorem. This was P dx plus Q dy equals the double integral over d. D is just the region you're surrounding, so in this case, d would be this part. Of partial of q with respect to x minus partial of p with respect to y and a. But this equation is meant for positive orientation. If you know it's a negative orientation, which it is, because it's clockwise, you put a negative sign on. So there's a negative sign on here. This is for negative orientation. Okay. So the first part was to draw this, put in your arrows, shade the stuff, and the second part is to set up the double integral, which means I want you to set up the right side. So polar coordinates was obviously the best way to do that. In 4a, the p was actually 2y, the q was minus 3x. A lot of people forgot the negative. So p sub y is 2, q sub x is minus 3. So qx minus py is just minus 5. Right? So your double integral is just going to be minus, this is 4, the double integral over the region of minus 5 dA, which is negative of minus 5. If you're doing polar, the dA becomes r dr d theta. And the theta would be what? And a lot of people messed up the theta as well. For the second quadrant, do you remember what the theta was? Pi over 2 to pi. The radius is what?
0 to 2.
0 to 2. So that was your guide. So this ends up being 5 times the double integral of 0 of pi over 2 to pi 0 to 2 of r dr d theta. Well, this guy just gives you the area of the circle, the area of the region, right? This is the area of the quarter circle. I mean, you could do it the long way, but I think it'll be easier just knowing that. So this is just 5 times, what's the area of a circle? Pi r squared, what's the r?
Radius.
2. So
So it's pi r squared, but you divide by 4 because there's only a quarter.
True.
So this would cancel that, you get 5 pi.
Easy way.
I have a question.
Yes.
All right. For Green's theorem, if you're traversing the circle in the clockwise fashion, so instead of putting the negative in front, you switch the bounds on the.
Like do pi to pi over 2.
Yeah. Can you do that?
You can do that. Just, I usually encourage students not to do that, but that's because they usually switch the bound and put the negative sign. They do both.
It makes sense.
It doesn't, no. If you're switching this guy, don't put the negative sign. It's one or the other. Right? Because if you switch this and then put a negative sign, you're negating the negation of your thing. So you just end up right where you started. So that would be wrong. So I usually just tell people, just set it up for positive orientation and then put a negative sign in front. If you want to be fancy and switch this, you should know not to put a negative sign in front, but that's probably asking too much.
Yeah, can I do from negative 2 to 0 for the radius?
For the
Radius? Yeah, for the R.
No, no. In polar, your R is non-negative. The setup for polar coordinates, R is non-negative.
Question, are we allowed to flip around the second integral if you wanted to? We can, because we can just flip it, right?
You could flip that one.
Okay, okay.
Yeah. I don't want to get all complicated and flipping limits on things. That's too much. Okay. Figuring out the quadrants is hard enough, obviously. So, what's the general form of a line?
Which one?
What does a line look like?
Curve.
Constant times.
I'm not talking about the algebra and y equals mx plus b part. Calc 3. A straight line in 3 dimensions, what does it look like? Yes.
X minus x naught over a. Do the same thing for y over b.
Yeah, that's harmonic from symmetrical.
This is called the symmetric version for the equation of a line, right? It's rarely used, and in fact in 392 I don't think you ever see that one. You might see it rarely in Calc 3, but it's very not a typical form. Giving me as a vector function, because usually in our line of work we're going to parameterize this thing into a vector function. So how do I know R of t is a straight line? Tell me what I should write. Just tell me. X naught plus AT, Y naught plus BT, Z naught plus CT, right? That is the equation of a line. What is the X naught, Y naught, Z naught? Point on the line.
You use the line orientation instead of vector.
Come again?
You put a vector, so point.
Points, and you can think of them as position vectors.
Yeah, I mean, that's
So you could do that. It's fine. Either way here. Like to put it in the equation of a line, you think of the point as a position vector to get the vector equation. Because technically you can't add a point to a vector, so you just think of it as a position vector. And what's the ABC?
your direction vector.
Direction vector of the line. Okay. What does a plane look like?
Plane. Okay, well, it looks like the gradient.
Just tell me what to write on. Hurry up. A times x minus x naught. A lot of people tend to forget the 0. Okay, that's a plane.
And often ABC is just gradient of some function.
What is ABC here?
Normal vector.
Normal vector to the plane.
Which can be found using plane right here.
Right? And x naught, y naught, again, is a point on the plane. What sign of pi over 6? You're taking too long. What sign of pi over 6?
That's for 2.
No. What sign of pi over 6?
That's
1/2.
Sign of pi over 6.
1/2.
That's not easy to say. What sign of pi over 6? You expect the whole class to be like, oh, it's 1/2 to 1. That's right.
Oh, because pi over 6 is 30.
How do you integrate that?
Oh, you use the Pythagoras theorem. So.
Double angle formula, right? 1/2, 1 plus cosine 2x dx, right? Easy integration from there.
Sure.
What if I did this? How do you integrate that?
Break it up.
Into what?
Into
Cosine
cosine
Squared
and
minus sine squared
sine
x and
squared,
cosine.
and then make cosine squared equal to 1 minus sine squared.
Yes, good. What about how do you integrate that?
Do the same thing.
What is u?
Actually, yeah, you do u sub. U sub.
U sub for what?
Actually, no. Yeah,
Would you pull one out and then use
Pull what?
Would you pull a cosine out?
You separate a cosine.
yeah.
And then
And then it's sine 2 pi. I mean, and then sine 2t, isn't it? Sine 2t over 2.
No. After that, you change the cosine to 1 minus sine squared u sub.
Yeah.
U
Oh, yeah,
cosine.
definitely.
What's the integral of ln x?
I want to So it's not. It's actually
Derivative of ln x is 1 over x. What's the integral of ln x?
X ln x minus
X ln x minus x. You should have that memorized. If you don't have it memorized, how do you figure it out? Integration by parts. What are your parts?
ln x and 1
You should tell me who is the u, who is the dv. If I'm finding the integral of ln x, who is the u, who is the dv?
the u is ln x, the dv is d1.
U
The ln x, the ln x, the u is dv is d1.
Wait, no. U is ln x.
U is ln x, dv is dx.
Or 1.
How do you integrate that? What are your parts?
U is x, and sine is dv.
How do you integrate that?
Same thing, but you can always integrate arctan, can't you?
Arctan? There's arctan.
I mean, arcsine. There's arcsine, I think it's 1 over radical.
Just tell me how you do it.
Okay.
By parts. What are the parts?
U is x, sine of negative 1 is dv. And integrate sine using 1 over radical 1 minus x squared.
Okay.
What was that?
How do you integrate tangent inverse?
Tangent inverse 1 over 1 plus x squared.
1
1 over 1 minus 1 over 1
No.
plus x squared.
The integral of 1 over 1
Yeah.
plus x squared
Oh,
equals
God.
tan inverse.
Yes.
You're telling me the
Secant
derivative.
squared. Secant squared.
It's not secant squared.
Oh, yeah, that's tangent. Oh my god. I don't think I learned that, did I?
Use integration by parts.
It's integration by parts. Again, what are the
Yeah.
parts?
Oh, I see.
Oh, arctan would be
The
Arctan would be u, dv would be dx.
Yeah, that's correct.
What's tan inverse of 1?
Tan inverse of 1.
You're taking too long. What's tan inverse of 1?
It's radical. No, pi over 4. Pi over 4. Pi over 4.
pi over 4.
Pi over 4. Okay, I have a straight line from 0 to minus 5 comma 7. How do I parameterize that?
With time? With
What is it?
With time or what?
Straight line from here to here. What's the param?
Okay.
One person. Quiet, everyone. You, what is it? What are the limits on your t?
We actually do.
I want to parameterize the intersection of this with the plane that. How do I do it?
Wait.
Plug
in 4 for the x. No.
2 sine theta.
Solve for one of them and plug it into the other equation.
What?
X and Y, then solve for
What is it?
So x
Cosine
X
theta.
is 2 cosine
Sine theta.
theta. 2 sine theta.
Plus 1 cosine theta sine theta.
1 cosine theta.
1, 2 cosine theta plus
1
1
minus
cosine
2
theta
cosine.
plus 2 sine theta.
Minus.
Minus.
You guys are taking too long.
Okay, how about that?
What's cosine of pi over 3?
Pi over 3 is vertical. No, 1 over vertical 3. No.
It's 60.
It's
Cosine of 60 is 1/2.
correct.
No.
You should know it without having to convert to
3 over 2.
Square root 3 over 2.
Root 3 over 2.
Vertical 3 over 2.
Okay, the questions, you see the questions I was asking just now? Those are examples of questions where you virtually should take no time to figure out. You should see it and you know what to do. Right? If I explore the equation of a line, you should just know what it is. If I go to an algebra class and I pick out a random algebra student and I say, student, what is the equation of a line? They will say, Jhevon, I cannot tell a lie. It is y equals mx plus b. M is the slope, b is the y-intercept. If I ask you, what is the equation of a line? Why can't you do the same thing? You know why they would know this? Because they're an algebra student, and it's the equation of a line. That's why. Lines show up all the time. You learn about a line, within a couple days you write down the equation half a dozen times, maybe more. These are not things you think about. When we give you time for tests, we're not giving you time to figure that out. We're giving you time to actually do the integration. We don't expect you to take any time to parameterize something, or to figure out what the equation of a line should look like, or to figure out what is sine of pi over 6. That's not what you have time for. That's something you know. Just like if I come to you and I say, what is your name? You can answer right away. That's how if I say, what is the equation of a line? You should be able to answer right away. If you can't, you're not studying. I'm tired of the silly pre-calc mistakes, algebra mistakes. This is 392. Those mistakes are behind you. 2 years behind you. Okay. Anyway, set my warnings. Let's move on. So last time we started 13.6. Well, we barely started because, we had to have our talk.
Okay.
So let's continue with 13.6. Let's try to finish it today. So 13.6, we're going to learn to parameterize two-dimensional surfaces. So recall, let's start back. R of UV equals X of UV, Y of UV, Z of UV, parameterizes a 2D surface in 3 space.
Professor,
Yes.
from what I recall from chapter 13.6, the only minutes that you can figure out the vectors on the plane, they don't really enable you to just do it yourself. Looking at the equation, you can figure out the vectors on the plane. So.
If it's a plane. But
Yeah.
our surfaces are going to, in general, be a lot more general than a plane.
Okay.
Right. If they give you a plane, yeah, you can just look at the coefficient of x, y, z. That's your normal.
Yeah.
vector. Right. Here we're going to do things a lot more general. I don't just care about plane. I care about spheres, paraboloids, any kind of cylinder, any random surface that I can concoct out of my mind. So that's what we're heading for. How do you find the normal vectors, especially from parameterized form, etc. Right. So we learned that to parameterize a two-dimensional space, a surface, you need 2 variables.
Sure.
To parameterize a solid, you need 3 variables, etc. Right? Every time the dimension goes up, you need 1 more variable.
Sure.
So parameterizing curves, you just need R of t, only one guy, R of t. To parameterize surfaces, you need 2 variables, u and v. Okay. So that's where I pretty much defined what a parametric surface is, and of course x equals this, y equals that, z equals that gives the parametric equations, right? So that's pretty much where we left off last time, and I explained how you get the points. And let's cover some examples. And general. So here's something. Identify and sketch this surface. I'm not going to give you a general form just yet. I'm just going to see where we are in interpreting these things. Suppose I told you a surface was 3 cosine u, 3 sine u, v, where my u goes between 0 and 2 pi, my v goes between 0 and 5. What surface is that?
Cylinder.
Cylinder, right?
V. And radius.
Cylinder.
And radius 3.
What's the radius?
3.
Radius is 3. What's the height?
B.
1.
5.
Oh, sorry,
Height is
5.
5.
Yeah.
Right? You're plotting this
Yeah.
guy. It would look like a cylinder running along the z-axis, but you're going to cut it off when your z is 0, which gives you the guy in the xy plane, up to when z is 5. Right? So this is actually this surface, a hollow cylinder.
Hollow?
Yes, it's hollow. There's nothing inside.
Okay.
It's a 2D surface. Right? So it's always the skin is what we're parameterizing with something like this.
A cone is definitely a surface, right?
What?
A cone is
Yes, a
definitely-
cone is a surface.
But I heard that it's possible to have two things with, like cone is iffy, sorry.
No, it's not. They're all just the skin.
Alright.
If you have two variables, you're parameterized a two-dimensional surface, which means at most you can do the skin. You can't get a solid with it. Right? If you worry about solids, that's what integration helps you with. Okay, so this illustrates a general form. So again, I'm going to tell you about general forms, right? Because when I was parameterizing, I told you about three general forms. What were they? Parameterizing curves. What are the general forms that we look for?
There's using trig, and then there's using the general form saying that x is equal to x, y is equal to y, and z is equal to function x or y.
What's the general forms? What are the three types of curves that I'm going to ask you to parameterize? Circle, straight line, anything else.
Yeah.
With circles, you use sine and cosine. With straight lines, you use the formula I gave you. With anything else, solve for an independent variable, blah, blah, blah. Right? You guys should know this by heart. Right? So you go on a test and they say, parameterize a straight line. You immediately know what to do. Right? Parameterize a circle. You immediately know what to do. Parameterize this other random curve that's not a circle, straight line. You immediately know what to do. Right? In the same way, for two-dimensional surfaces, there are going to be some general forms where if they say cylinder, you should immediately know what to do, right? Or sphere, you immediately know what to do. Plane, you immediately know what to do, right? So we're going to talk about those general forms. So this illustrates a general form. This is the radius r. Here r is. This is a mistake that people always make. They sometimes forget that here, if you put an r here, it's constant. Your variables are u and v. So something like this would be, example, r of uv equals r cosine u, r sine u, and v. Right? R constant. V depends on z. V really equals z, right? So whatever the z values are. So whenever I tell you a limit for v, I'm giving you a limit for z. It's really giving you the height, right? Of course, one thing you're going to have to remember in 3-space is you can always shuffle things around, right? So these can be permuted. Example, r of uv equals r cosine u v, r sine u is also a cylinder. How would it look?
It would be going up and down the y-axis.
It's going to run along the y, because the y is defining the height.
Indeed.
So you have the cylinder running like along the y-axis, right? So depending on where this guy is, it just tells you what side the cylinder is lying on. But basically, we see r cosine, r sine, and just another thing, it's a cylinder, right? And you can permute these in any order. It doesn't have to always be x is the cosine, y is the sine. You have to be flexible here. Yes. I think
when we parameterize lines, we use the variable t. Now, in general, does that variable t represent time?
it can be interpreted that way. Sure.
So, what would be the interpretation of u and v?
Parameters.
Yeah, I made that.
Parameters. Like in the equation of a line or any curve, t is interpreted as a parameter.
As
right?
what?
Parameter. Just it's a parameter. That's what it's general for.
I
Now sometimes you can just, based on what you're doing, you can assume that it's time, right? Because usually you're going to want, there's a particle traveling along this curve, and you parameterize in terms
Well,
of time.
the thing is, I learned in V to be vectors on a surface of a plane. So there are two vectors. Yeah, there are two vectors on a surface of a plane.
Hold one
so.
constant, and you get like a cross-sectional, like, I guess, curve of the thing.
That's true, yes. Because if you hold one constant, then you'd have a single parameter, and then you're back to a vector curve situation. Good, but we're not going to deal too much into that.
Yeah, man.
We're just going to use that concept to figure out the general form of a normal vector, which I asked for as the bonus point in the bonus problem in this.
Oh, and
Right?
also,
So these are called right circular cylinders, right? Because there are many forms of cylinders.
Professor,
Yes.
say if you had like 1 plus r cosine u, something like that, does that shift it over a little bit?
Okay. Come again?
If you had like 1 plus r cosine u, would that shift it over?
That shifts the
And-
center. Yes.
In the x.
Yes.
Could you give us like a circle, like, could you tell us to parameterize a circle that's not centered at the origin?
They don't ask that. I mean, this parameterization is centered.
Yeah, but would you do that?
This would be center 0, 0, z, right? For any z value.
Yeah.
You just have circles.
Yeah, but would you do that to us, for us? I mean,
No.
good.
I don't think I ever actually do that. Yeah.
When do you know when to use r as a variable or r as a constant? Like when do you know?
Well,
Right.
Because
So
right now r is going from 0 to 2.
R?
Yeah.
No.
I mean,
R is
0 to
constant
3.
2. R is a 3. R is a constant 3. Your R in this case would be here. Your variables are u and v.
well, it depends it's hollow, that's really why.
You can't make R a variable because then you get a solid.
Oh, okay.
Right?
So
If
that's
your
the
R
point
ranges
of
from
it.
0 all the way up to 3, then you'd have all these mini cylinders filled in and going
Exactly,
down.
and it becomes a...
Right? If I only want the surface itself, the skin, I have to go to the maximum R. So R is just fixed at 3.
Yeah, so it's just fixed
So
curve.
it depends on how you want to look at it. Right? So in general, if I'm doing a surface with the U and V, then my R here would be constant. That gives me the outer skin.
And if you weren't doing a surface, if you were doing
Volume?
a solid, then you will have 3 variables, not just...
Yes, you'd have 3 parameters. Yeah, that's what I mentioned. Every time you go up a dimension, you need one more variable
Oh,
to
okay.
keep track of it. So if I wanted to parameterize a solid cylinder, technically I'd be taking a level curve in 4 space, which ends up being a solid, which would end up being a 3-dimensional vector curve. Don't worry about that. We're not going to go there.
Do you need some sort of equation for the hyperbolic paraboloid?
No.
It's like UV.
It's going to be nice things. Cylinders, spheres,
Okay.
paraboloids.
Oh, so nothing.
You're not going to do hyperboloids.
So nothing interesting.
Another example.
Yeah.
This makes adjusting.
Oh, I think that's, yeah, here. Yeah, technically, I think it's like right.
What is that?
Surface of the sphere. Yeah.
Identify the surface. What is it?
Yeah, unit sphere. That's like, yeah, it's sphere that's hollow inside.
Demisphere. that's
Sphere. Radius is what?
1.
Right.
No, I know, it's a sphere with...
It's not a hemisphere.
It's just a sphere with a hollow inside.
Right. What if? And of course he's sketching. Blah blah blah. This is sphere. Radius 1. What if I said?
Hemispherical surface.
Hemisphere. Which hemisphere?
Top half.
The top half, right?
I think
What if I change this to pi?
And it would be
like a half hemisphere.
quarter.
Half hemisphere, right? So it's going to be like over here, just everything in the first octant and the fourth octant.
Question. I mean, some people do phi from negative pi over 2 to pi over 2, and some of them do
Phi in calculus 3, in our formulation of the setup, phi maximum range between 0 and pi.
Okay, because it depends on yeah. But can we still do it though, like negative pi over 2?
No, phi is 0.
Okay.
Okay, so this leads to another general form, sphere. So if I actually parameterize a sphere, you could always use this parameterization. Rho sine phi plus theta, rho phi sine theta, rho cosine phi. Rho is a constant. Radius of sphere. And the max ranges, theta is like 0 to 2 pi, and your phi would be 0 to pi. And the theta is just the same theta as in polar coordinates. So here you can mess around with it a little bit, like theta from minus pi over 2 to pi over 2, or something like that, if you want. If it is necessary.
Yeah, but not phi though?
Phi, no, it's always 0 to pi.
Oh, come on.
We never mess with the phi. Why complicate things, right? Same as in right? So if you see something that looks like that with a cosine and sine and something else in one of the other components, that's a cylinder. See something like this, we have two trig functions and you have a sine and cosine, and cosine here, you know that's a sphere. Right? So pay attention to these things.
Phi is along that's where you start from the z-axis?
Yeah.
Phi is the distance from the origin to the outer surface.
So it's the radius.
So it's like, well, it's not really a radius unless it's circular. Phi
Well,
is
no.
it's in general, it's the distance from the origin to the surface.
What's an angle though?
Come in?
It's what's an angle, kind of.
Phi is not an angle.
Phi.
Not phi, I mean rho.
Oh.
Were you asking about rho?
No, it's actually not.
Oh,
Phi. No, yeah.
what about it?
That's you go from the z-axis to you said 0 to pi.
Yes, phi is measured from the positive z-axis, and it extends down. It can
Yeah,
go as
well,
far
the
as
XY
the negative z-axis.
Yeah, the XY plane. The XY plane.
Okay, let's see here, so that was the general form for a sphere.
No, cone.
Now we're going to look at the general form of a plane. Get R of UV is equal to plus vector U times U. Use my variables. Vector A plus B vector V. Right? Here. A and B are vectors in the plane.
On the plane now.
When you're talking about parametrizing something, that's how it's going to be parameterized. So in your parameterization, you can't actually have like the normal vector sticking out. You actually need two vectors in the plane. Right? And it's actually equivalent. You can actually derive the original form from that. So I think I did. Did I do an example?
Are A and B necessarily perpendicular from each other, or no?
Come again?
Can A and B can be any angle away from each other, or
Yeah.
are they always? Okay.
Well, if they're parallel, it wouldn't really help.
No, but I'm saying if it's like perpendicular, it wouldn't matter.
No, no. A and B doesn't matter as long as they're non-parallel. So that would give you a plane. So if someone says, parameterize the plane that passes through this point and contains the vectors blah and blah, throw it in this way.
And yeah.
And again, random surfaces. This is sort of like the anything else category. We can parameterize surfaces and planes to So if you have a surface like z equals f of x, y, then you can parameterize it by just letting x be itself, y be itself, and then taking z equals f of x, y.
Yeah.
That's why I call it trivial parameterization. So you could say this is parameterized by r x y equals x comma y comma f of x, y. All right, so x and y here are your independent variables, and you can literally just leave them as themselves and parameterize according to the function.
And anything.
That will work for anything, yes. There's some trickiness involved if your thing is like a sphere, for example. Then if you solve for z, you actually get two functions.
Yeah.
So things like that is sort of
Positive,
where,
radical,
right. In cases like that, you'd probably use this parameterization.
Actually,
so
if you have a radical, I think near the xy plane, it begins to break off.
Near the xy plane.
Yeah, like if you would, for example, draw the circle on the computer, then near the xy plane it breaks off. You kind of have to use the parameterization.
I'm not sure.
I mean, the top half is correct, but it's kind of breaking off as the actual surface goes closer to the xy plane.
Yeah, well, you never actually really get there.
Oh, sure.
Yeah.
Are you going to do an example of a plane, like with numbers? Or can you?
Do you want an example?
Yeah, can you? Just understand it a little bit better.
Then you'd say R of uv would be equal to 1, 2, 3 plus u times 4, 5, 6 plus v times 7, 8, 9. You could write as 1 plus 4u plus 7v, comma 2 plus 5u plus 8v, comma 3 plus 6u plus 9v.
Don't we have to do a check to make sure you're not parallel first?
Yeah,
Generally,
but
yeah.
they're not.
Yeah.
But it's really interesting because if you look at the one-dimensional case, it's just v naught plus some number times g, and in this case, you're actually doing the same thing with two values.
Right. I mean, if your v was a constant, right, because your plane is like this. If you set any one of these parameters constant, you get back into a vector curve, and the vector curves in the plane are straight lines. So if this is a constant, you're able to combine it with this, and you get the form for a straight line. Right? If you leave the v constant, then you get lines going like this way. If you let the u constant, you get lines going the other way.
It depends what direction.
So it depends on what direction your u and v are, which will not always be clear from the context.
It could technically be a diagonal along the surface, can't it?
Yeah, it'll just be a line that's in the plane.
Yeah, correct.
Let's see here, what else? So let's do an example here. Find the parameterization for
It's the top half of the sphere.
The upper half.
it's a cone, not a sphere.
No, it's top half of the sphere. Oh, I'm sorry, you're right. It's a cone. Top half of a cone, sorry.
It's
Right, cone,
it's
yeah.
a cone.
If it was a constant, then it would be just a for it.
Right, so anyone want to tell me how to parameterize that? You asked about a cone earlier. Here, I'm going to do examples of how we do a cone.
I think an idea. X and y is equal to the vector.
Do it like that.
Oh, actually no. No,
All right. X equals x, y equals y,
no, there's another way to it.
and z equals the radical of x squared plus y squared.
First
That would be the trivial way you do it. You could say r of xy equals x, y, radical x squared plus y squared.
can you also say like u times x is equal to u times cosine of v, y is equal to u times sine of v, and z is equal to just u? I mean, yeah, u.
No, that wouldn't work.
Yes, it would.
No, it wouldn't. And it would be easy to see that it doesn't work, because if you plug your things into this equation, it would not be true. It's an easy check. If you wanted to, there are alternate ways to parameterize this, right? So what is another way you can think about parameterizing it, which is sort of going to what he wants to get to? If you wanted to get trig functions, how would you do it? Notice that if z equals the radical of x squared plus y squared, you can think of z squared equals x squared plus y squared. And what does this remind you
It's
of?
r. That's what I said.
It's a circle, right? This reminds you of a circle.
There's easy way r. It's exactly what I said.
Right? So it's not what you said. Reminds you of a circle, right? So here you'd think of the radius as the z, right? Right?
Yeah.
So your radius is actually changing. So you could say
And that's the coefficient of cosine and sine. Right?
you could use inspiration from polar equations. Your x is equal to r cosine theta, right? So it would be z cosine t or theta. Cosine theta, you can have your y equals z sine theta, and your z equals.
Yeah, and as I said,
And so then we'd have r of theta z equals which you're very close, but when you were saying it, you probably said it in haste and you actually switched the u's and the v's. You said it wrong. Right? So that's one way you could do it. But you have to remember one thing, right? Well, here you just know that if you're getting a radical, you can't take negative z. So here you restrict the z. So here, your z has to be greater than or equal to 0. So that would make sure that you only get the top half. So you know that you parameterize this. So if you wanted to have trig functions in there, you can. I don't know why. For our purposes, in general, if you have a cone, this would be the easier guy to work with. Let's see here. Yes.
Professor, can you, like, since UV is like the parameters that we use, can we just use UV instead of theta and V?
It doesn't matter. Like,
It does matter, right? So I could say, I could let, similar to what he was doing, let z equals u and x equals u cosine v, u sine v.
It's like
It's just like changing names, but just. Let's see, here's what else. Did I have another? No, that's the only example. I mean, your book does surfaces of revolution, but we're not going to cover that. We're not going to.
yeah, if it's count too.
So I don't really care. So yeah, so what you should get from this is there are general forms, circles, spheres, planes, and there is of course your default, right? If you can't figure out what the hell it is, you sort of parameterize in terms of the independent variable. Yep.
Wait, is that a half cone and that's a
Yeah, it
double
is.
cone?
This would be a half cone, yes.
half.
If I allowed z to be negative
Then,
as well, then I'd get the bottom half as well.
the thing is, I've heard some stuff about the cone though. I've heard that because there's a point at which it's not a plane anymore. It's a point. It's not really considered a surface. Like at the origin, it's a point. It's no longer a surface. So
No.
so they don't really consider surfaces of that.
Yeah, because you're thinking of it at a single point. It's not a surface. For a surface, they have to be a range of
No, I
values.
mean that's just what my professor of calculus 3 told me, that the cone isn't really considered a surface because it's not because at a certain point it's not a surface anymore.
Right. That's talking about level curves, which is very different from a
Okay.
surface. Right? If you set any z value, any constant z value, you just get a level curve. You don't get a surface. Right? So that's how you find a cone. If you're at the origin, you just get a point. If you're at the height of z equals 1, you have a circle of radius 1. Height of z equals 2, you get a circle of radius 2.
Yeah.
Z equals 3, you get a circle of radius 3. If you combine all these circles, you get a cone.
Wasn't
But
talking
any
about-
individual one
He
is
actually wasn't
not.
talking about the level curves. He was talking about the whole surface in general. It was when we were going over this chapter actually.
I think you misheard him. A cone is a surface.
Okay.
A cone is a surface. Don't let it be.
Well, wouldn't that be the same as the plane? Like if you make whatever constant, you get a line. Add all those lines together, you get the plane. So the same thing with the.
Yes, but each line,
Yeah.
you do not call it a
Yeah,
surface. It's a
yeah.
curve.
Yeah.
Right, but you can't say by that reasoning that a plane is not a surface.
Yeah, that's what I mean. Like,
It's made up of curves, but it is a surface. It's the same thing with a cone. It's made up of stacks of circles. Each of those are curves, but when you put them all together, you get a surface. Yes.
Quick question, short.
Huh?
I know this all is going
No, it doesn't.
but
That's the
if we
problem.
wanted now, we could set up triple integrals whenever we wanted to do the same.
Yeah, I mean that's what I'm saying.
It's actually, there's some differences in that, which when we go on, I'll talk more about that. So for example, if you're doing triple integrals involving these guys, your dv is not going to be like the dv's you remember.
Well,
So for example, if you parameterize in terms of theta and phi, and you're doing integrals in that, you wouldn't need to add the rho squared sine phi. We're going to go through the differences
Professor,
later on.
the reason why, I mean, I'm thinking the reason why he didn't consider it a cone surface was because at that point at 0, there's no partial derivatives at that point.
Okay.
You need partial derivatives in order to be for a surface.
To be a smooth surface, exactly.
So there aren't smooth. So there's non-smooth surfaces out there.
Of course.
What if you do?
Any surface with a sharp corner is a non-smooth surface, right? Let's take this surface here, like a top. Right? Like put a sheet on the floor and just pick it up by the needle point.
So it's not okay.
It's not a surface just because it has a needle point. It's still a surface.
What if you want to do an integral over the surface? Doesn't it have to have like the, because it's not smooth at that point, is it?
So you'd integrate around it. There are ways around it. Because I mean, I don't really want to get into these arguments, but if you're integrating around an open circle or a closed circle, what do you do different? Nothing. Right? Whether you can hit the boundary or you cannot hit the boundary, an integral doesn't care.
With what integral?
Any integral.
But, I mean, along the boundary or on the actual domain? enclosed by
if I know my region is an open circle and I'm setting up a polar integral, the r still goes from 0 to the outer radius. It doesn't matter if the actual boundary is included or not.
Yeah.
If you take an integral and you just remove one slice, you remove 0 area. The integral doesn't care. Right? So let's see, where are we now? Okay, let's talk about finding normal vectors and tangent points of parametric surfaces, because that's going to be pretty much important. So we already know this, how to do this. We should know how to do this in Calc 3, but now we're going to do it, redo Calc 3 in the parametrized version.
Okay.
Right? So finding, and then I'm going to also show that this is going to be equivalent to what we have done in Calc 3, which is going to show you when you're doing the Calc 3 way, there are going to be certain instances where the Calc 3 way is easier, and there are certain instances where this way is easier. And I'm going to talk about that and show that they're actually equivalent. Finding normal vectors and tangent points. Okay. So let R of UV be a surface. Define the following. Let me actually write it out. X of UV, Y of UV, Z of UV. Define the following. R sub U of UV is just the partial derivative of all the components with respect to U. So this is partial of X with respect to U, comma partial of Y with respect to U, partial of Z with respect to U. And similarly, R sub V of UV is partial of X with respect to V, partial of Y with respect to V, partial of Z with respect to V. Now, these give vectors on the surface in the direction of U and V. Right, so similarly, when you're doing calculus and they said you're taking the derivative, you're talking about the slope, which you can sort of think of something that's telling you direction, right? Like the rise over run. It sort of tells you, is the line pointing up, is the line pointing down? The vectors you can use in a very similar way. So if you have some random surface, and at this point, your RU would give you the direction that your U is pointing in. And your RV is going to give you the direction that your V is pointing in, right? So this is pointing in the V direction. Right? This is pointing in the U direction. Right? So if you want to think of the trivial parametrization case where I let X be itself and Y be itself, it means that R sub X would actually point in the direction of the X axis. R sub Y would point in the direction of the Y axis. Right? So knowing that, how do you think you'd actually find a normal vector?
Cross product?
Cross product. Right. With simple arguments, we can get that N is equal to RU cross RV gives the normal vector if you want the normal vector at a particular point, you just plug in that particular point, uv. Let's see. And let me mention something, since it's obviously a concern in this course. So this is the idea of the whole smooth curves thing. Except, unless your derivatives, we allow them to be 0 at the boundaries, like, or extreme points like here. But in the surfaces, if I'm integrating over like here, then I don't want any sharp corners. I only allow it at the endpoints, because integrals don't care about endpoints really. If you take out the endpoints of any integral, the integral will not change. Integration is what we're going to want to be able to do with these guys.
Well, by not change, what do you mean by that? Because if you continue to take away endpoints, eventually your line will get smaller.
Mm-hmm.
I mean, if you continue to take away endpoints, eventually your line will get smaller, won't it?
No. If I have this rectangle of 1 to 2, the height is 2. If I take the integral over this rectangle, what do I get?
2 minus 3, 4.
4. You get 4. What if I say, you know what? Take out this line 1. What's the area now?
Okay.
Still 4. Right? So I don't care if at the edges it's not smooth. Doesn't matter. It's not going to affect my integral. Right? If you remove a line has no area. So if you remove a line from your thing, it's not going to change anything.
Well, maybe it's just negligible.
Huh?
Maybe it's just negligible.
Yes, it's negligible.
Okay.
But technically, theoretically, it's 0. Okay, so I think I want to do an example. So at this point, if you know the normal vector on a point, right, so another example, just to bring it back to Calc 3, if I use the trivial parameterization, let x be itself, y be itself, then this guy will actually give me the gradient to the surface. So since we know how to find n by this formula, very important, you should have that memorized.
Okay.
It'll be easy to find the tangent plane to the surface, provided we're given a point to find the tangent plane. I'm going to do another example. So that's how you find the normal vector, and now I'm going to show you how to find the tangent plane. What does a plane look like?
It has wings.
Yeah, very funny. Yeah, write that on your exam. Exactly. Scott jokes. Yeah, you are. Okay, so let's do an example. Find the equation of the tangent plane to R u v equals u v u plus v squared. at the point 2, 1, 3. And I don't think we have more time for that. So. This example then we leave. And 13.6 is not finished, so no homework on Monday.
Nice. Let's study your recount.
It may not be so good when Wednesday hits. You get all that homework between Monday and Wednesday.
Okay. By the way, what kind of surface is this?
General surface.
Flat surface.
Do you know? This would be the surface Z equals x plus y squared.
Oh, is that
So if you were to write the scalar equation of this thing, that's how you write it, right? Your x is u and your y is v. That's basically it.
Yeah, so it's the general surface.
Anyway, so yeah, this is parameterized using the trivial parameterization. Anyway, let's continue. So we know what we're going to use for the normal, right? We're going to find RU, RV, and we're going to need to find RU cross RV. Well, let's do that.
You don't need to do that, do you? Because you can express it in terms of z, and then you can take z to the other side, and then
That's true.
Yes, that's true.
So,
Yes, I want to do the example this way, but yes. If you see it, you could say this is z equals x plus y squared, and then calc 3 way to find the tangent thing. But in general, you're not going to give them something easy where you be able to solve it. Or you're going to be given something where it's not worth solving for. So I just want to give an easy example here because I'm introducing the topic, so I don't want to get too crazy. Okay. So what RU and RV look like?
RU is 1, 0, 1.
Okay. What about RV?
0, 1, 2.
0, 1, 2V, right? But see, this guy is a variable in here, right?
Yes,
and
plug it in.
I would recommend not to, if you're doing something like this, not to carry the variables. Actually, plug in the point that you want, right? So you want to evaluate this at 2, 1, 3. Evaluate this at 2, 1, 3. This one, of course, is not going to change because it's a constant vector. But what are we going to plug in to get 2, 1, 3?
1.
To get 2, 1, 3, u must be equal to what? V must be equal to what?
You must be equal to 2, you must equal to 1.
Right. You said this guy equal to that point and match them up, right? So u must be 2, the v must be 1, and this would obviously be 1 plus 1.
Yeah,
1 plus
2 plus
2
1.
plus 1, right? So you get 3. So your u must be 2, your v must be 1, right? And so for RU at the point at the 2, 1, 3, and RV at the point 2, 1, 3. This is just going to be 1, 0, 1. This is going to be 0, 1. So I plug in v equals 1 into here, and I just get 2, right? So the important thing in here is you have to remember that this point is actually x, y, z. Right? It's not u and v. So you have to first figure out what u and v needs to be, and then you plug them into this formula. And then from here, this would mean that the normal vector is going to be just the cross product of these guys. Which is going to be what?
Negative 1, negative 2, and 1.
Negative 1, if you do that, you get 2, negative 2, and if you do that, you get 1.
So it should be 1 and 2v. So
This implies, what does the plane look like?
it's down in the x-y direction, but pointing out from the z direction.
Can't you hold the other two at 0 and then just plot points?
The general form of a plane is what?
Times x minus x naught.
A times x minus x naught
Oh, you
plus
that's
b
drawing
times
it.
y minus y naught plus c times z minus z naught equals 0. We know that a, b, c is the normal vector, and we know that x, y, z is the point. So let me ask again, what does the tangent bring us?
Minus, after x minus.
Minus 1 times x minus 2 minus 2 times y minus 1 and 3 and 1 times z minus 3 equals 0. This is the tangent. Right? So we know the point. It's 2, 1, 3. So you're putting 2, 1, 3. You also know the normal vectors. Minus 1, minus 2, 1. Minus 1, minus 2, 1.
Depending on the thing is, for 100 calculus 3, if two planes are parallel but they're at the same point, then
If they're parallel, but what?
but have the same points, even if the known vector is
If they're
not,
parallel and have the same points, they're
then
the same
they're the
thing.
same plane. Even if the known vector is pointing in this direction or the opposite direction, it doesn't
Yeah,
matter.
normal it doesn't matter. It can be going in the exact opposite direction. It's considered.
So answer could be the negation of that, and it would be correct.
Yeah, I could put plus 1
Okay,
minus
sure,
here,
sure.
but
Because before you said that if we did the cross product the other way, then it would be technically incorrect.
no.
Yes, you did. Yeah, you did a while ago. I asked you if I can do it this way and then this way. I said no, it has to be this way and this way. When you introducing cross products.
You asked me about a normal vector and I said it matters the order?
Yeah, you did.
No, I didn't.
You said about the cross product.
Yeah.
The order.
Yeah, the order of the cross product matters.
And can we do
Matter.
it?
The order of a
But
cross
the negative
product
and the
matters.
positive direction, you just go in two different directions.
It doesn't matter, it's a normal vector.
Yeah, it should matter.
It's still a normal vector.
It's still perpendicular to the plane.
It's only in different directions.
I wouldn't say that. If you have u cross v, and this is equal to the negative of v cross u, right?
Yeah.
These are parallel. Why would it matter which one I take?
I don't know, but before you said it though.
It's the direction.
Maybe I misinterpreted you or you misinterpreted me.
Okay.
It doesn't matter.
Okay.
And clearly when